Hello, this is the third installment of our AI lecture in Pathfinding, and this time it is about the actual pathfinding algorithm called, from the name of its inventor, Dijkstra Algorithm. Previously in the series, you should have learned how to create a representation of the level layout using a graph, and also how to make your NPC follow the route using waypoints. These are both essential prerequisites for the Dijkstra algorithm, so if you haven't watched them, you should. You should also have completed practice programming activities, getting the spider follow a simple waymarked route. At the moment, this route only contains the initial and final node, with the spider taking a brave shortcut between them. This is because instead of a full pathfinding algorithm, we only use the simple start function, which only pushes these two nodes, start and goal. Simple as it is still a starting point for our Dijkstra implementation, and in particular, it already has all the input we need. So the graph itself, the indices for the start and goal nodes, and a structure, a vector of integers, which will collect, or which will be used to collect all the intermediary nodes, creating the shortest route. So, Dijkstra algorithm was created and published by a Dutch computer scientist, Edgar Dijkstra, in 1956. It was originally a purely graph processing algorithm, known then as the shortest path first algorithm, or SPF. Which is not very surprising considering that gaming wasn't particularly popular in 1956. Actually, the first game ever created was written 6 years later, and it had no AI characters. The name Dijkstra algorithm was only adopted many years later, and it wasn't the name originally intended by Dijkstra for his algorithm. I will explain the operation of the algorithm using an example task of finding the shortest path from the node number 3, which is here, and this is the closest to the spider, to the node number 8, which is here. And this is the graph representation of the level layout, with clearly shown the start node and the final or the goal node. The edges of this graph are labeled with the numbers which are the cost of traversing between the nodes. This cost is basically Euclidean distance. The algorithm works by spreading out of the start node along the available connections in all possible directions. At each visited node, the algorithm stores the best cost so far and keeps the record of the direction it came from. This cost so far is the total cost of traversing from the start node to the node which is currently visited. Eventually, the algorithm will reach the goal node. At this stage, the best cost so far will be known, and the complete path may be reconstructed from the recorded directions, working backwards from the final node to the start. At each iteration of the algorithm, one node is selected as the currently visited node. Besides that, all the nodes are divided into 3 categories. Initially, all nodes are considered as unvisited. Whilst the algorithm progresses, some nodes will be first open and then closed. So we have 3 categories of nodes: unvisited, open, and closed. The initial step of the algorithm is to add the start node, so in our case this is the node number 3, to the open list, with the cost so far equal to 0 and the connection equal to -1, which means no previous connections. And now we are ready to start the first iteration of the algorithm. Each iteration starts by finding the open node with the minimum cost. In this case it must be node number 3, which becomes our current node. Moving on, we will now visit all nodes adjacent to the current node and store each visited node as an open node. So the first node to visit is the node number 1, and it's stored in the open nodes with its cost 143, and the connection is equal to the current node, so connection is node number 3. Going on to node number 2 with cost 192 and connection again the current node number 3. The final node to add to the open nodes is the node number 5, cost so far 304, connection 3. Now we can close the current node by adding it to the closed nodes list, and we have to remove it from the open nodes. And this concludes the iteration number 1. Now we will go ahead to the iteration number 2. In each iteration, we first of all find the open node with the minimum cost. This time it has to be node number 1, with the cost so far 143. And that's our new current cost. And as previously, we will visit all nodes adjacent to the current one. So the first node to visit this time is node number 0. It hasn't been previously visited, so we add it to the open nodes. But its cost so far is calculated as a sum of the current node cost so far, so 143, and the additional cost of reaching the new node from the current node, so it's 143 plus 128, it's 271. This means that this is the total cost of reaching the node number 0 from the start node. And the connection for this node is our current node, node number 1. Next node to visit is the node number 2. This node has been already visited and its cost so far is 192. Its new cost would be our cost so far 143 plus the additional cost of reaching the new node 181. 143 plus 181 is 324. It's much more than the cost so far for this node, so we will ignore it. We will not update the node. If you just look at the graph, it is quite obvious that this was not the good route to node number 2. The previous route, the direct route this way, with the cost 192, was a lot better than the currently tried route via node number 1. So this is the reason why the algorithm does not update cost so far for this node. The last node to visit in this iteration is node number 3, And we have the same situation here. The original cost so far of this node was 0, so whatever we had now, it couldn't compete with 0. In the Dijkstra algorithm, closed nodes are never updated because this algorithm guarantees that closed nodes have already the optimal route calculated. Okay, we are now ready to nearly finish the iteration. The last thing, we have to close the current node. We do it by adding it to the closed nodes list and removing it from the open nodes. The iteration number 2 is now complete. So going on to iteration number 3, the new current node is node number 2 with the lowest value of cost so far, 192. So we are now changing to a new current node, number 2, and the first adjacent node to visit is number 1. New cost for number 1 would be 373. It's our cost so far, 192, plus additional cost to reach number 1, 181. And it's much more than the currently registered cost so far, 143. Besides, node number 1 is a closed node, and we know by now that Dijkstra algorithm never updates closed nodes. So we reject this new cost, we don't update the node. The next node to visit is node number 3. It's again a closed node, so we can ignore it and go straight to the node number 4, which is previously unvisited. So we will add this node to the open nodes with cost so far 576, which is our current cost so far, 192, plus the additional value 384. Connection for this new node is our current node number 2. And this is the end of the iteration, so we only close the current node number 2, so it appears in the closed nodes and disappears from the open nodes. We are now ready to start the iteration number 4. The new current node is number 0, with the cost so far 271, so we are now here. The first adjacent node is node number 1, but this one is a closed node, so no update. And the second one is number 17, previously unvisited, added to open nodes with cost so far 527. Connection is now, the current node is 0. Okay. Close the current node by adding it to the closed and removing from the open. We are ready for iteration number 5. The new current node is node number 5. It is here. And let's go with adjacent nodes. Node number 3 is closed, so unupdated. Node number 4 is previously visited open node. The new cost is our current cost so far, 304, plus additional cost to reach the node number 4, 208, it's 512. But the previous cost was 576. Wow, we have found a better route. Our new cost is 512, which is better than the cost so far stored in the system. So we will now replace the cost so far with the new calculated cost 512, and we also change to the new connection to our current node, node number 5. And if you look at the shape of our graph, it becomes quite obvious. Our previously optimal route to node number 4 was from 3 across to 2 and here. and we have right now discovered a shortcut. It's a diagonal line, so this connection should indeed be a little bit shorter. Okay, we have visited number 4. There is one more node left. It's number 6, previously unvisited, added to the open nodes. The iteration is nearly completed. We will just add the current node to the closed, closing the current node, ready to start another iteration. Iteration number 6. The new current node is also number 6. The first node to visit is number 4. Previous cost was 512. The new cost is 534, so it's rejected. The next node is number 5. It's a previously closed node, so no updates. And we also have to visit node number 7, previously unvisited, so added to the open nodes with cost so far 598. Closing the node number 6. Okay, and going on to the iteration number 7. The new current node is the node number 4. That's the node with the minimum cost so far, and the adjacent ones are number 2, but it is closed, so no updates. Number 5, another closed one, no updates. Number 6, another closed one, no updates. And number 8, which is incidentally our destination, our goal node, but it's for now it's just an unvisited node, so it's been added to the open nodes with cost so far 704 and connection to the current node number 4. This iteration is now nearly done, so we will only add the current node to the closed nodes and move on to the iteration number 8. In the iteration number 8, our new current node at the cost so far 598 is the node number 7, and from here we can visit node number 6, which is closed, so no update, and node number 9, which is a new one, so added to the open nodes. Close the number 7, and the iteration is over. The next iteration, iteration number 9, the new current node with the cost so far 527 is the node number 17. So at the other end of the graph, it's here, and from here we should visit the adjacent node number 0, but it's closed, so no update, and node number 16. It's a previously unvisited node. Add to open nodes and close the number 17. The iteration is completed. The next iteration is the 10th iteration, and for the new current node is promoted the node number 8 with cost so far 704. And now, with node number 8 as the current one, the goal node has been reached. Yes, this is our final destination. We don't need any more iterations, and the algorithm is ready now to collect all our nodes, starting from the goal node, working backwards to recreate the shortest path from node 3 to node 8. In order to do that, we check the connection registered for node number 8, that's number 4. Okay, so the previous link in our path, final path, is node number 4. For the node number 4, the connection was number 5, so the previous link is number 5. For number 5, previous connection was number 3, so we go back to number 3, and for the number 3 connection was -1, no connection, so we have recreated the full shortest path from node number 3 to node number 8. The NPC should follow number 3, number 5, number 4, number 8, with a total cost of 704. Let's now summarize our findings in the form of a short pseudocode of the Dijkstra algorithm. The first operation to be performed even before we start all the iterations in the first initialization by adding the start node to the open list with cost so far equal 0 and connection equal to -1. With this single element in the open list, we can start the iterations, and the classical Dijkstra algorithm will continue these operations as long as the open list is not empty, if there are any open nodes. The first operation within each iteration must be finding the current node as the open node with the minimum cost so far. If it happens that the current node is equal to the goal node, we can break the iteration because we have just calculated the shortest path. But if this is not the case, we move on to finding all the adjacent nodes to the current node, and for each adjacent node we first of all calculate the new cost so far for this adjacent node as the current node's cost so far plus the additional cost to reach the adjacent node from the current node. And now, if the adjacent node is already open and its existing cost so far is not better than the new cost so far, there is nothing more to do here, and we can continue or restart the iteration with the next adjacent node. But if not, this means that we have just found a new route to the adjacent node, so its cost so far becomes new cost so far, and its connection becomes the current node index. If in addition to this the adjacent node is yet unvisited, we'll mark it as open and add it to the open list. These are all operations to be done on the consecutive adjacent nodes. When we finish browsing through all the adjacent nodes, we can close the iteration by marking current node as closed and removing this node from the open list. Optionally, you can add it to the closed list as well. This concludes the main iterations of this algorithm, and we also have some final operations here. If after all iterations the open list is empty, this means that we have used all the possible options, all the possible routes, not finding the shortest path. So path is not found and we can return false. But if there are any unused items, this would include at least the goal node. This means that the path has been found, so we just collect the path and return true. I will now conclude the presentation of the Dijkstra algorithm with a few implementation remarks. So, first of all, your connection structure may remain without any modifications, but the node structure will require a few additional variables such as cost so far, connection, and also open and closed Boolean flags. This is the extended version of Dijkstra algorithm pseudocode, which can be found in Canvas. It is not yet C++ code, but it has much more details than the shorter version presented earlier in this video, and should be very helpful when you implement the algorithm, particularly in conjunction with these remarks here on the implementation of the open list. First of all, the best way of implementing the open list is using the stl list of integer values to store just node indices in the list. Now, to add a new item, use the pushback function available in stl. To test if the collection list is empty, use the size function. To find the minimum element, use the standard stl algorithm min element. There was an example of its use in the waypointing part of this lecture, so I won't repeat all the details here, just mention that we use a slightly different predicate, logical predicate here, which makes it possible to find the element with the minimum cost so far. And finally, to delete item, use the erase function, also available in stl. Note that the successful implementation of the Dijkstra algorithm does not require using a separate list of closed nodes. I showed such a list in this presentation only to facilitate your understanding of the algorithm, but in the real implementation you only need to remember to remove the closed nodes from the open list, and it will work fine for you. Now it's the time to program, to implement your own version of Dijkstra algorithm for pathfinding. This concludes the Dijkstra algorithm part of this pathfinding lecture. After completing your programming task, please continue to the final installment, which will provide information on how you can improve on the data representations for pathfinding, and also how you can step forward from the Dijkstra algorithm to some even more effective or efficient solutions, such as the A* algorithm. And I am already saying goodbye to you, and thank you for watching.